This is just a little video to give you a bit of a head start on your first chemistry assessment task. It's based on a lot of frequently asked questions from previous years. And the first one of these is about using this term temperature gradient in your first answer. You've probably heard the word gradient in maths before, but it applies in many other places apart from maths. And I'm not going to tell you exactly what a temperature gradient is, but I'm going to give you some examples that might help illustrate what we mean by temperature gradient. And the first one, the most obvious one, is here we've got a topographic map, and it shows changes in altitude. It shows the contour lines. So if you could imagine yourself walking from, say, this point here, which is at 700 meters, up the hill towards this point here, which is at 800 meters, you can imagine, if I just transcribe that down here, as you're walking from point to point, what will be happening if this is your altitude? You'd be going up and up and up and up and up. You'd be walking up a gradient. All it means is that as you're moving across the ground in like horizontal distance, you're also moving up in altitude at the same time, and we call this a gradient. You'd be walking up the gradient because the altitude is changing as your horizontal displacement is changing. You could also have a gradient in pressure. This is a barometric pressure map of Australia, and you might be coming from, say, over here in Western Australia, Northern Territory, where the pressure is 1,000, over across to New South Wales, where it's currently 1,016. You're walking from points A to B. It'd be a very long walk, but just for the sake of the argument, let's just say you're walking along that way, and you might be carrying a balloon for some reason. So as you're walking from point A to B, you'd be starting off at a pressure of 1,000 kilopascals, ending up at a pressure of, say, 1,016 kilopascals, and as you're walking from Western Australia to New South Wales, you'd slowly notice an increase in pressure, and that would be a pressure gradient because the pressure is changing as your horizontal displacement is changing. This could also be considered relevant to your first question, explaining how the fractional distillation column works. That little balloon you were carrying, it might suddenly explode if the pressure got, say, above 1,010 kilopascals, and so you'd be walking along. As soon as that temperature gradient took you to a place where the pressure was 1,010 kilopascals, your balloon might explode. Okay, so the pressure gradient here has some sort of very important points along the way where things might happen, similar to your temperature gradient inside your fractional distillation column. A bit cryptic, I know, but hopefully that helps you get a better picture of what I mean by a temperature gradient, and you might start thinking about why a temperature gradient is so important inside a fractional distillation column. Okay, on to some more tips. First thing is alkanes. In part 2b, you've got to go through and figure out how to name hydrocarbons, and I'm going to give you a few tips here. These are the most commonly asked questions about hydrocarbons. And the first one is, they're called hydrocarbons because they contain hydrogen and carbon, and that's it. Hydrocarbons, only two elements inside hydrocarbons, and they're very, very common and very, very important compounds. And the most basic type of hydrocarbons are alkanes. Alkanes are just chains of carbon atoms with single bonds between them. This ending ane, this suffix anes, means single bonds, or single carbon-carbon bonds only. So there's a chain of 5 carbon atoms in a row. Now we're going to learn very soon that carbon's in group 4 of the periodic table. It's got 4 valence electrons, and therefore it always forms 4 bonds. So that means every one of these carbons here in this chain wants to have 4 bonds. So what that means is each of these carbons, all the remaining bonds, are bonded with hydrogen. So these ones in the middle of the chain, which have already got a bond on either side with the carbon, end up with 2 hydrogens. The ones at the end of the chain will end up with 3 hydrogens. And there we have, that's one of our example hydrocarbons, and we call this hydrocarbon pentane. We've said the ane represents the fact that all these bonds in the chain are all single bonds. That's why it's called ane. And pent, you've probably heard of something like a pentagon before, or a pentagram. Pent means 5, and there are 5 carbons. 1, 2, 3, 4, 5. So when a chemist hears the word pentane, they immediately think 5 carbons in a chain with only single bonds between them. That's what pentane means. There is a general formula for alkanes. If you think about the mathematics of how this chain would work, if you've got n carbons in the chain, you'll always have twice as many hydrogens plus 2. And that's because every carbon in the chain has 2 hydrogens attached to it, but the chain's got 2 ends, so there's 2 extra carbons. So every carbon in the chain's got 2 hydrogens plus 1 extra one at the 2 ends. And that's what an alkane is. As far as the naming is concerned, you need to be very aware of these, and by the end of this assessment task you should know these off by heart. Meth, eth, prop, bute, pent, hex, hept, oct. That's all we need to know for preliminary chemistry. After that it does go non for 9 and dec for 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but you only need to know up to 8. And most of them are pretty simple because you should know octagons, hexagons, pentagons. Hept is a bit different, just something to remember. Hept sort of similar to sept. I'm not sure if they call them septagons or heptagons in mathematics. Bute's a bit strange. Prop's a bit strange if you follow rugby. Number 3 is the prop, which is similar to prop, I suppose. Eth is 2, and meth is 1. And that's the first style of hydrocarbon. There are 2 more you need to know for your assessment task, and they are alkenes and alkynes. Now they both start similarly, they both start with alk, which means they're the hydrocarbon chains, but alkenes, when you see an ENE in the name of an alkene, that means you've got one place in the chain where there's 2 carbons joined together by a double bond. The carbons are bonded to each other twice, and if you ever see a YNE suffix, that's for the alkynes. That means there's one spot in the chain where there's 2 carbons that have a triple bond or bonded to each other 3 times somewhere in the chain. We call these special parts of the chain the functional groups. If you've got this chain, for example, which would be an example of an alkane, it's got 1, 2, 3, 4 carbons. This would be called butane. And you compared it to these 2. Once again, each carbon has got 4 bonds. So 4, 4. This one's already got 3 bonds. It only needs 1 more hydrogen. This one has already got 2. It only needs 2 more hydrogens. Note that I'm not drawing the hydrogens in here to save time, but you need to draw the hydrogens in for your assessment task. And then you've got another chain here which we could draw like this. Got 3 hydrogens there, that one needs 2. This carbon's already got 4 bonds, this one only needs 1 more bonds. So these 4 compounds are very similar, but they are different in the fact that this one's all got single bonds, this one has some spot in the chain with a double bond, and this one's got some spot in the chain with a triple bond. So we give these a different name. This would be called butene, but just be aware we're going to clarify this name a little bit later on when we get to the next slide, and this one will be called butane. And once again we're going to clarify this name a little bit more on the next slide. But the main thing I want you to understand now is that they're all have the prefix bute because they've got 4 carbons. This one's butane, single bonds. This one has got 1 double bond. There's a double bond here in the chain, so it's called butene. This one's got a triple bond in the chain, so we call it butane. So you need to know anes, enes, and ines stand for alkanes, alkenes, and alkynes, single bonds, double bonds, and triple bonds in the chain. Now these 3 compounds, even though they are very, very similar, they are distinct in their physical and chemical properties, and it's because of this difference in the bonding. And the difference in the bonding is either the double bond or the triple bond. And as we learn more and more about hydrocarbons and different sorts of hydrocarbon compounds, if there's something different in the chain, different from the simple alkane, it's going to change the properties. So this double bond here changes the properties quite significantly. The triple bond here changes the properties quite significantly. And we call these extra parts of the molecule, the part of the molecule that controls the properties, we call it a functional group. Now a homologous series, that is a whole series of compounds with the same functional group. Okay, so a homologous series has the same functional group. The functional group of this will be the single carbon bonds. And that means other compounds in this series, other compounds in butane's homologous group will be methane, ethane, propane, pentane, etc., etc. Other compounds in butane's homologous series would be ethene, propene, etc., etc., etc. And down here, other compounds in butyne's homologous series would be ethine, propyne, etc., etc., etc. So a functional group is just that special part of the molecule which is different to the alkane, which controls the properties of that particular series of compounds, and all hydrocarbons that have the same functional group are called a homologous series. One thing you might want to think about, I'm not going to tell you why, but we didn't put methene or methine in there. It's a very important reason why we didn't. That's something to think about for your assessment task. But we'll move on now to isomers. We said on the previous slide we were going to look into a bit more detail of why we're going to change the name a little bit. So let's look at that butene example again. I'll draw butene on the board. And there is an example of butene. We would call this C4, 1, 2, 3, 4, 5, 6, 7, 8, H8. 4 carbons, 8 hydrogens. Now similar to the alkenes also have a general formula. For every n carbons, you'll always have twice as many hydrogens. You can figure that out yourselves if you like. That's just a simple fact. But we could also arrange 4 carbons and 8 hydrogens in a slightly different way. We could also draw a very similar structure that looked like this. Once again, we've got 4 carbons and 8 hydrogens. In both chains, they are both hydrocarbon chains. They've both only got carbons and hydrogens. They've both got a double bond. So we could call them both butene. 4 carbons with a double bond. However, it's pretty obvious they're not the same compound. They are different. One's got the double bond at the end of the chain, and one's got the double bond in the middle of the chain. And we call these two types of compounds, we call them isomers. An isomer is just a compound with the same molecular formula. So both these compounds have the same molecular formula, C4H8, but they've got different structural formula. And it's pretty obvious they've got different structural formula. One of them has got the double bond at the end of the chain. One of them has got the double bond in the middle of the chain. So they're called isomers of each other. And because there's 2 isomers of butene, we need to give them different names. And the way we name them is, it's pretty simple. We just put a number in there to show where that double bond is. For this first chain up here, if we think about it, where could the double bonds be? There's 1, 2, 3 places where the double bond can be. And for that reason, we call this one but-1-ene, which tells the people reading this, but means there's 4 carbons. The 1 tells us there's something in the first position and that this double bond. So that tells me when I'm reading this, there's 4 carbons and it's got a double bond in the first spot in the chain. So that's but-1-ene. In the old days, well, not that long ago actually, they would have called this 1-butene. And if you ever see that, they both mean exactly the same thing, just that the modern standard puts the 1 closer to the ene, because we're saying the double bond is in the first position, so we put that 1 as close to the name of the double bond as we possibly can. But sometimes in textbooks, particularly if they're more than 5 years old, you'll see them written as 1-butene. Well, this makes it pretty obvious down here. This is 1, 2, 3. We're going to call this but-2-ene. And there we have, they're the 2 isomers. And don't forget, same molecular formula, different structural formula. There are 2 isomers of butene. And that means anytime you've got a compound that's got more than 1 isomer, you have to be very careful to put these 1s and 2s in there to talk specifically at which isomer you are talking about. It's a very common trap for preliminary chemistry students to forget to number their isomers. One thing we didn't put up there, and you might be thinking, is why didn't I put but-3-ene up there? Well, let's just draw what but-3-ene would look like. One, 2, 3, double bond on the third, C. Once again, we've still got C4H8. You might be tempted, and when you see this written on a page, it's a common trick. Teachers will try and trick you with this in exams. Not that I do anything like that, of course, but teachers might put that on an exam, say no compound, and you might be jumping straight away to say but-3-ene. Because clearly, you've got 4 carbons, so it's but. You've got a double bond, so it's ene, and this double bond is on the 1 to the 3rd spot. The only thing is you've fallen for a simple trap, because you've got to realise these molecules aren't static on a page. They're in 3-dimensional space, constantly moving around, and we've got to ask ourselves, is this really any different to this compound, which we've already seen? And if you think about it, we've already named this one, we've called this but-1-ene. If you think about it, are these 2 molecules actually any different to each other? Because if all I did was rotate this molecule 180 degrees in space, it'd be pretty obvious that these 2 molecules are identical. And because they're identical, they're not different isomers, they are actually the same compound, okay? All it means is this one's got a double bond at the end of the chain, this one's got a double bond at the end of the chain. They are exactly the same. There is no such thing as butene. This is called but1ene. So be very careful when naming isomers. You've got to realize that you actually have to number from the closest end. The easiest way to overcome this problem of naming is to always think, no matter where the functional group is, here's our functional group, you always number from the end closest to the functional group. If we did that, we would have straight away saw this is the first carbon, that's the first position, that's the second position, that's the third position. We wouldn't have done this in the first place. You don't have to number left to right in chemistry. You number from the end closest to the functional group. And therefore we number from this end. It's definitely called but1ene. Now that short video hopefully helps to clarify some questions you might have in your assessment task. You're always welcome though to ask more questions at any time, as you know.